Let's take a minute and review a couple of the problems that you guys have been working over: frequency, wavelength, sound, resonance, okay, music essentially. The first one I want to take a look at is the challenge problem. Now, yesterday in class, for some reason, I couldn't solve this problem, but then as soon as everybody left, I was like, oh, this isn't hard at all. Okay, but I do want to go through it, make sure you guys kind of understand. Okay, determine the tension Ft in a violin string of length L that has mass M, okay, and will play a fundamental note at the same frequency as a closed pipe, also of length L. Okay, so essentially we have a string on a violin. Okay, it's L units in length, and we have a closed pipe, also of length L. Okay, and we want to play them so that their fundamental frequency, or tune them so that their fundamental frequency is the same. Now, the interesting thing about frequency is it depends only on the source of the wave. Now remember, V equals wavelength times frequency, but also, okay, when you have a string, V equals the square root of the tension divided by mass per unit length, okay? And we're going to use both of these. Now, the reason I was having a hard time is I was trying to make these two velocities the same, and that's not the case, okay? This we're going to call U for now. This is the speed of the wave on the string, not the speed of the wave through the air. This is the speed of a sound wave through air, okay? Now, an air column has that speed, but a wave on a string has a different speed. Okay, so what we want to do is we want to say, well, what is the fundamental frequency for the pipe? Okay. Well, since it's a closed pipe, it's forced to have a node on one side and an antinode on the other, and that means its wavelength, the longest wavelength that'll fit on it, is 4L. Now, if we use this to go into this equation, we can solve for the fundamental frequency, and we can say V equals 4L times F, okay, where this is F1, the fundamental frequency of the vibration or the note that's produced. Okay, and if we solve that for F1, then F1 equals the speed of sound, V, divided by 4L. Okay, now what we want is we want the frequency for this vibrating string to be the same. Okay, but the issue over here is its wavelength, okay, for the string, it's forced to have a half a wave fit. Okay, so the fundamental frequency over here is going to correspond to the wavelength of the longest wave, but that's only 2L. Okay, now this is where you got to pay a little bit of attention. This wave is actually moving on this string. Okay, and so we're going to use the same kind of equation. U equals wavelength times frequency, but this time, okay, U is the speed of the wave on the string, not the speed of the wave through a column of air. Okay, and so now I have U equals 2L, okay, F1. But what we want is we want this frequency right here to match this frequency over here. Okay, and so I'm going to go ahead and sub that in. I'm going to say, okay, well, that means U equals 2L times V over 4L, and happily this length cancels that length. 2 over 4 is V. Okay, so I get U equals 1/2 V. Okay, now that's related the two speeds together, and now I can go into this equation and actually solve for what I need the tension in the string to be. So I'm going to say, okay, 1/2 V equals U equals the square root of tension divided by mass per unit length. Okay, I don't really care about the U, so I'm just going to square both sides. 1/4, right, half squared, V squared equals Ft divided by mass per unit length. Okay, now go ahead and multiply both sides by mass per unit length, and I get the tension in the string, Ft, is equal to mv squared over 4L. Okay, so the tension in the string, if we're going to tune it up, needs to be the mass of the string times the speed of sound in air squared divided by 4 times the length of the string. Okay, which the second part of this problem actually uses. It says, okay, what is the tension in the string of mass 1 gram? So M equals 1 gram. Be careful with that unit. And 40 centimeters long, so L equals 40 centimeters. Okay, again, be careful with that unit. That plays the same note as a closed pipe of the same length. Okay, well, what we have then is our mass and our length, and we know V. V is the speed of sound in air. So all we have to do is plug in all these things. So 1 gram equals 0.001 kilograms. 40 centimeters equals 0.4 meters. And so I have Ft equals 0.001 times 343 squared over 4 times 0.4. And if you work the math out on that, it's right around 74 newtons. Okay, so that's 16 or so pounds of tension. So it's a fairly tight string, but okay, a little bit weird that you had 2 different speeds, but you have to remember the speed of a wave depends on the medium it's moving through. This wave in a pipe is moving through air, the velocity is 343. This wave is moving through a string, and that velocity is a little bit different. Now, I also assigned a few problems out of the book yesterday. These ones were math problems, right? And let me know if you have any questions on any of them. I did want to run through an example on one of them. Okay, and number 78, 78 is a organ problem. It says the lowest note on an organ is 4 hertz. Okay, the lowest note, that's code for fundamental frequency, right? This is the lowest we can make it. Okay, and since it's an organ, it's a pipe organ, it's moving through, the sound is moving through air. We know the speed of sound in air is 343 meters per second. Okay, but we're supposed to get a length, which means we need to relate this to length somehow. Well, we know the fundamental frequency is going to correlate to the fundamental wavelength, right? Well, on an open pipe, the longest possible wave is 2L. Okay, because it's got a node at both ends. So half a wave will fit in the pipe, which means the wave is twice as long as the pipe. Okay, so 2L is our fundamental length, and so we can just use V equals wavelength times frequency and then plug in these things that we have. 343 equals 2L, because I don't know what L is, times 16.4. Okay, so 343 equals 32.8 times L, and if we divide both sides by 32.8, we're going to end up with right around 10.5 meters or so. Okay, so the length of this pipe is 10.5 meters. That's like a 31-foot long pipe. Okay, so that's kind of big. B says, what is the pitch if the same organ pipe is closed? Okay, well, if you close it, what does that mean? That means one side gets to be an antinode. That means the length, the fundamental length here, is not 2L, it's 4L. Okay, and essentially what we've done is we've just doubled the length of the wave of this fundamental. This just got multiplied by 2. So that means this one has to get cut in half. So our pitch of our lower note now is going to be like 8.2 hertz because the wave that fits in there is twice as long. Okay, now you can work out the math using the same process, but to me it's like, okay, well, if we double one, the other one has to get cut in half. Okay, so hopefully these problems are making sense. Let me know if you need any help.